Hello guys, this is Shailesh. Here I am going to present something about the zero knowledge proofs. It's not much in detail, but I am trying to cover it up as pictorial as possible, which I have taken from different sources here. So yes, first of all, when you say zero knowledge proof, in my previous videos I have told you that it's part of being used in MPCs, and also APC is also going to be part of zero knowledge proof. So it is something like an intersection of both the circuits or both the technologies actually intersect between each other. And ZK is basically, yes, in the confidential transactions we use ZKs, and also in the ZK rollups. That means that Ethereum rollups, or reducing the cost of transactions for all those blockchain related things and non-blockchain related things, we use this zero knowledge proofs, and a lot of mathematical topics are involved in this, especially the algebraic part. But it is not geometry. It is not the mathematical geometry that we used to study in the +2 or in the different degree exams actually. Because in the geometry proof, you are not proving anything to a different party there, and there is no communication mechanism, or there is no query that is happening between a second party to the first party who is trying to prove it. So the proof, zero knowledge proof, is a system, and it's not just the only the mathematical theorems. So that's the basic difference. So please don't confuse between the geometry proof and the proof system. Now, when it comes to the ZK or the zero knowledge, it means that somebody is trying to send the information without actually sharing those information to that party actually. That means that prover is sending something to verifier, but verifier will not get the exact thing what the prover has it. So it's something like prover's age is, let's say, of 45, but verifier will be able to know that the prover's age is greater than 40 and between 50. So he will not be able to know the exact input or exact statement. So whichever the statement that prover has, or prover is generating the proof, that will not be shared with the verifier, but the verifier will be able to know, or there is a probabilistic mechanism here. That means that probability is there. It's not 100%, but verifier with its inputs or with its queries will be able to get those answers, whether the prover is honest or not, based on the proof that he's sending it. So this has been used in many different parts of blockchain, and the basic mathematics that's being used is the hash commitments, Peterson commitments, polynomial commitments. These are the different types of commitments, but especially the Peterson or the polynomial commitments are much more famous. But there are two different types of ZKs actually, which is one is the interactive and another one is the non-interactive. The interactive one, that means that prover and verifier is sitting in a in an area where both can communicate with each other directly. There is no third party there, and so this is an interactive system here, interactive zero knowledge. And here, once the prover sends, or once the prover is communicating with the verifier queries that particular elements, that the final proof is generated only once the communication between the prover and verifier has been done. So it will be like many iterations that will happen between the prover and verifier here, and only then the final proof is generated. So in many cases the proof size will be much more heavier, and it will take more time to generate. That's one thing. But the advantage of it is that, yes, the verifier is fully interacting with the prover, but it increases the gas cost in blockchain. That's one of the things. But in non-interactive, which is being used in many practical blockchain applications, where there is a intermediate, which is the random oracle model, which will be an intermediate and which will be interacting with the prover and the between the prover, and it will, based on the hash function or the random generators, actually it will issue the queries, and based on that the proof gets generated. And let's say for 1000 transactions, the ROM or the intermediate is enough to generate one single proof, and that gets aggregated, and that gets passed on to the verifier, which is sitting in a blockchain maybe. That's a good thing of non-interactive, but in the interactive ones, it will happen always in the off-chain part, where the prover and verifier should be sitting in the off-chain environment. In the non-interactive ones, both the prover will be sitting in the off-chain environment, and the verifier will be sitting in the on-chain environment. So the ROM plays an intermediate role here, which aggregates and which sends the proof to the verifier. So there are many different types of proofs, many different types of zero knowledges are there, starting from range proofs, bullet proofs, sigma proofs, which we discussed in the confidential transaction section. And then there is a ZK Stack. ZK Stack is much more famous. Stack and snarks are much more famous here because that's been used. ZK Stack is mostly post-quantum secure, and because it's using the hash functions, and it follows the different PQC related things. In ZK Snark, there is a TDTP, that is a trusted third party, which will generate the key, which is responsible for generating the key. And so in many cases, the MPC is required to generate the keys, actually, CRS, common reference strings. In the Snark case, in the ZK interactive knowledge, that's mostly the interactive ones which I explained. In the concurrent ZKP, this is basically with having concurrent proofs that's getting generated, and then later it's getting aggregated. And the lattice cryptography is being used in the lattice-based ZKP. And then the later versions of Plonk, where Plonky, Plonkup, Plonky2, and all things are being used, where certain parts of Stack and certain parts of Snark is being used here. That is, the KZG plus FRI commitment schemes are used, and both the polynomial commitments are basically used here, which means that it has a complex set of calculations, and there should be a lot of optimizations that works on top of these things. With the Peterson commitments, which is basically the bulletproof and sigma proofs, it's basically the proof size is much less, and it's less complicated, and the computation is not that much needed as compared to the polynomial commitment. And then comes the designated verifier. That means that based on the designated verifier address, the prover will know that which verifier is going to verify the public address, and based on that, only that verifier will be able to verify the proofs. So that's about the designated verifier. When it comes to the bullet proofs, which is much easy one, and it's been used in many of the smart contracts, because the transactions or the depending on the transaction sizes, actually the proofs will be much more smaller, and there is no much complex calculations that's involved in it, where you need an instant transactions that needs to be done. For that, you use the bullet proofs. Then you come up with the there are different versions of bullet proofs. First one is the range proof, which was invented in 2015 by Greg Maxwell, which means that for the proofs are generated for a particular range of numbers, and based on that it gets the proof gets generated. So let's say but the problem was that for a 40 byte transaction, the 4000 bytes is needed, 4000 bytes of proof size is needed for this range proofs. That was the disadvantage. Then the bulletproof comes up, which is in the 2018, which contains the Peterson commitment, and based on that, it gets the proofs get generated, which means you don't need a TTTP, you don't need a common reference strings or any other keys. It gets the proof gets generated, and the size also gets reduced from 4000 bytes to 600 bytes, which is much more cheaper compared to the range proof. And then the same thing happens with Bulletproof Plus and Bulletproof Plus Plus, where in the years of 2020 and 2023, this was being found. And the latest one is of Plus Plus, actually, which means that around 450 bytes is required. With the help of proof of aggregation, actually, you can batch a lot of transactions, which will generate a compact proof for a good amount of transactions, and that will be getting published into the smart contract, which means it reduces time in proof generation and also in the verification process also, because the proof is being sent into the Ethereum call data, and the call data gas cost is also much less when it comes to the plus thing. So yes, so this is about the ZKP used in graph isomorphism. You can go and check the Manuel Blum paper actually there, and you can check it out how the isomorphism works in the graph, which means that you have you have two graphs, and whether those graphs with different vertices, in the case these two graphs actually, you can see that, and these two graphs whether they are isomorphic or not, whether they are similar, whether the structures of these two graphs are similar or not, without giving the functional program or without exchanging the functional programs to the verifier, the prover should prove that. Which means that it needs to generate a third graph based on this. There should be a function which generates a third graph here, which means that from here it is getting generated into the new graph, which means that this graph is isomorphic to this graph. So there's a bisection type of things, and with those things actually this isomorphism is being defined there, and the verifier tries to find out that this graph which has been shared with the verifier, whether it is isomorphic to the second graph, to the other graphs that prover has it. So it in the form of iterations like 1, 2, 3, 4 different iterations, the verifier will be trying to ask the questions with each vertices and with each edges, that how it is isomorphic, whether it is isomorphic or not. And that proves that the prover knows exactly what is happening here. Prover knows, or prover has sent a right proof that the graphs that he has between which are these two graphs are similar, and he has the exact function to prove that this particular two graphs are isomorphic. So without sharing those secret functions, actually the verifier will be able to know that with a proper interactive mode of things. So this is basically an interactive thing, that what you're seeing, interactive zero knowledge, where without transferring any of those attributes or any of those structural informations, actually the verifier will be able to understand that both of these two graphs are isomorphic. This is basically the thing that where the we have our own mobiles, and in that we have a passport, driver's license, and national ID, and this can be verified by a central authority or by a decentralized authority here without getting our exact passport, by having an app inserted in our passport, inserted in our mobile, and that will interact with the verifier, where the verifier will be asking the questions, and based on that actually the prover or the passport holder will be able to send the default proof, send the exact proof to the verifier. So the passport holder should not be, or is not required to share the the authenticated sources, exact sources. Without that, without sharing the exact information, actually the verifier will be able to understand it and verify it. So it's all about the decentralized verification, where you're not sharing any of your personal details with them. So this is about the formal verification. Formal verification, it's nothing but the ZK circuits that we develop, as we discussed here, with different circuits, where if you have to prove something to the verifier, you need to develop a circuit, a mathematical circuit, which will be converted into the program using Rust, Golang, or OCaml, or any type of programs. The circuits are developed, where the circuit expects a witness program, and based on the constraints that's been added in the circuit, actually based on that it validates it and generates a proper proof. And there are different equations, there are different mathematical equations that's there, that we will discuss in the coming videos, like in the Stark, what all commitment schemes you have in Snark, Hyperplonk, Sonic, or Halo 2, what are the problems, or what are the solutions to each and every problem in each and every circuit. There are different circuits. So for those circuits, this has to be checked, that it has to be properly audited, like any other smart contracts are getting audited, where how the auditing happen. I mean, if you audit your circuit in a proper way with proper inputs and proper constraints, like have you added a proper constraint, or is there any way where the hackers will be able to manage and get into your circuit and do hanky-panky things where your millions of coins can get transferred to a different account instead of the recipient account, whether that is possible or not. So these all things are being done in the auditing phase, and so it is always good that in auditing you use a formal verification tool or formal verification manual mechanism where you can check your constraints and your the witness generator, where there are different types of constraints there here, like transition constraint, boundary constraint, memory constraints, so the terminal constraints. So this type of constraints can be checked with the formal verification tool by having a specification. So based on the input programs that you are passing into the circuit, or based on the witness program that you're passing into the circuit, actually you generate a specification. Either you automatically generate it using a tool, or you manually generate a spec. And based on the spec, there are different there are different tools that's there for, like in the interactive theorem prover or using pushback mechanisms. There are different proof assistant tools are there, and different other tools are there, manual tools are there, where you can generate the invariants and you can write the invariants, you can write the assert statements that this should satisfy, and only then the from one particular phase to the other phase the workflow can transfer. So the constraint checks, the invariants, these all things has to be added, and also the polynomial commitment checks, where whether this particular the condition is being satisfied or not. If you are a developer, you will be able to understand like how you write your unit test cases, how you write your require command in the Solidity, the similar to that, but in much more detailed way, in a mathematical way. Actually, the specifications are written. And there are many other tools, like in a virtual machine itself, many people, many companies have added this formal verification tool, like MoveVM, and MoveVM is using a Boogie, that is the SMT solver tool, that is the CVC3 CVC or the Z3 tool actually that's been used there, where once you write a move program using, which is also a Rust based thing, your specifications are generated, you can modify the specs, and also you can write the invariants in that program, and based on that invariants actually you the formal verification tool works accordingly. So you can override it, you can write that invariants, new invariants based on the equations that you have, and finally you get the result. And if it is not passing, it will give you a bug, and then you need to do the iterations there. So there are different tools here. One is that yes, you need to do it in the ZK circuit about your different constraints and your polynomial commitments or Peterson logics, whichever you are writing there, how you write the checks. And in the smart contract where you do the verification, there also you need to write the checks of is there any other parameters that has to be checked for each and every variables that's been used. You need to write an invariant for that. So there are different tools that's been used, like Ursus plus T, which is based on Rust verification. Ursus is also based on Rust. Daphne, it's basically a DSL which generates the formal verification specification. The Satora prover, it's a very famous tool among the auditors actually. So most of them are based on Rust, but yes, you will be able to find different other DSL based tools, also based on OCaml and also based on Lurk. So it depends all on how you want to use it, like whether you want to use this manual COQ or what you say, the other lean based programming mechanisms. This all things depends on it, but the formal verification is a very good way of preventing different attacks that can happen, and this is being used basically mostly in the ZK VM side, but this can be used in different other mechanisms wherever you use ZKs. Yeah. So in this video, this is the these are the topics that I want to introduce. Thank you for watching.